Have you ever heard of a planet so cold and so far away that sunlight barely touches it, yet it somehow found a way to cool itself down even more? Because that is exactly what Pluto appears to be doing, and the telescope that caught it in the act was never supposed to reveal something this weird so clearly. Before we go deeper, do this with me right now. Tap like if you love real space mysteries, subscribe if you want the truth behind the headlines, and share this with one friend who still thinks Pluto is just a frozen rock. For years, Pluto lived in the public imagination as a kind of cosmic afterthought. First, it was the mysterious ninth planet. Then it became the most famous object in astronomy to get demoted. And after that, a lot of people quietly filed it away in their minds as a small, distant world that probably did not matter very much. Cold, tiny, empty, done. But the farther science has pushed into the outer solar system, the more that simple picture started to break apart. Pluto did not turn out to be boring. It turned out to be one of the strangest places we have ever studied. And now the James Webb Space Telescope has added something even more unsettling to Pluto's story. It has helped confirm that Pluto's atmosphere is not just sitting there in the dark, passively freezing. It is behaving in a way scientists had never confirmed anywhere else in the solar system. Pluto's hazy sky seems to be acting almost like a cooling machine, taking in sunlight and then shedding energy back into space so efficiently that the atmosphere ends up colder than expected. That should not feel normal. On most worlds, sunlight is already precious. On Pluto, it is barely there at all. And yet, even that weak light may be enough to power a climate trick that makes this world colder still. That is the heart of this story. Not just that James Webb looked at Pluto, but that when it did, Pluto answered with something so unusual that scientists had to describe it as a new kind of climate behavior. To understand why that matters, we need to go back to the beginning, because Pluto has always had a talent for embarrassing our assumptions. When Clyde Tombaugh discovered Pluto in 1930, it instantly became legendary. Here was a new world found at the very edge of the known solar system, a tiny moving dot hidden among fixed stars. For decades, that dot carried an almost mythic weight. Pluto was distant enough to feel mysterious and familiar enough to belong on school posters, classroom mobiles, and every diagram of the solar system people grew up memorizing. The problem was that for most of that time, we were not really looking at Pluto as a world. We were looking at it as a blur. Even with powerful telescopes, Pluto was frustratingly hard to resolve. Scientists could track its orbit. They could measure changes in brightness. They could make educated guesses about its size, its reflectivity, and maybe the presence of frosts on its surface. But the real Pluto remained hidden behind distance, darkness, and very limited data. That created a strange situation. Pluto became famous long before it became understood. And when understanding finally started to arrive, it did not make Pluto simpler. It made Pluto weirder. In 2006, Pluto lost its official title as the ninth planet. That reclassification became a cultural event, but scientifically, it distracted from something more important. The real question was never whether Pluto fit neatly into a category people preferred. The real question was what kind of world Pluto actually was. 9 years later, that question got the first serious answer. In July of 2015, NASA's New Horizons spacecraft reached Pluto after traveling for more than 9 years across the solar system. It was not going there to orbit. It was not going there to land. It had one shot, one flyby, one fast, brief chance to collect as much data as possible before it kept going into the Kuiper Belt. And what it saw changed everything. Instead of a dead little ice ball, New Horizons revealed a planet-sized contradiction. There were towering mountains made of water ice, so frozen and rigid that they behaved more like rock than the slippery ice we know on Earth. There was a vast, bright plain shaped like a heart, known as Sputnik Planitia, made largely of nitrogen ice, and so wide that it became one of the defining features of Pluto's face. There were layered hazes in the atmosphere. There were signs of active surface processes. There were landscapes that looked young, which is a serious surprise on a world expected to be ancient, battered, and geologically quiet. Pluto did not look finished. Pluto looked alive in a geological sense, like a place where processes were still unfolding. That alone would have been enough to rescue Pluto from irrelevance. But the deeper shock was this. New Horizons only gave us a passing glance. As historic as that mission was, it was still a flyby. A brilliant, once-in-history snapshot. It gave us stunning images and invaluable measurements, but it also left behind a long list of unanswered questions. How stable was Pluto's atmosphere over time? How exactly were its surface ices moving and changing? What role did its atmospheric haze really play? What chemistry was happening there now, not just during those few precious moments in 2015? To answer those questions, scientists needed something different from a spacecraft screaming past at thousands of miles per hour. They needed a telescope that could sit far away, stare carefully, and read the faint thermal and chemical fingerprints of a world almost 4 billion miles from the sun. That is where James Webb enters the story. A lot of people hear Space Telescope and think of sharper pictures. But Webb's real power is deeper than that. It is not just about seeing objects. It is about decoding the light coming from them. Webb works strongly in infrared, the part of the spectrum that lets scientists detect heat, chemistry, and subtle physical behavior that visible light images cannot reveal on their own. That makes Webb perfect for worlds like Pluto. Pluto is incredibly faint. It is small, cold, and very far away. On top of that, it sits close to Charon, its largest moon, and separating the two has not always been easy for older instruments. For years, scientists struggled to isolate Pluto's exact thermal signature. The signal was weak, the system was complicated, the tools were limited. Webb changed that. With its large mirror and sensitive instruments, especially in the mid-infrared, it could do something earlier observatories could not do well enough. It could separate Pluto's emission from Charon's and look for details hidden in that faint glow. And what it found did not just add detail, it confirmed a prediction that once sounded almost too strange to be true. Years before Webb launched, planetary scientist Xi Zhang proposed an idea that many people found hard to believe. After New Horizons showed Pluto wrapped in layers of haze, Zhang suggested that those haze particles were not just decorative. They were not just passive mist hanging over a frozen world. They might actually control the energy balance of Pluto's atmosphere. That sounds technical, but the idea is easier to understand than it seems. Think of a world getting a tiny amount of sunlight. You might expect anything in its atmosphere to help trap heat, at least a little, the way greenhouse gases or hazes can do in other places. But Zhang suggested Pluto's haze could be doing the opposite. The particles might absorb sunlight, warm up, and then radiate that energy away in infrared so efficiently that the atmosphere cools as a result. Not a blanket, a radiator, not insulation, a heat loss system. If that were true, Pluto would not just be cold because it is far away. Pluto would be participating in its own cooling. That was the bold claim. What Webb has now helped confirm is that this was not just a clever model, it was real. Recent research using Webb's measurements showed that Pluto's atmosphere is colder than earlier expectations, and that the haze particles appear to play the leading role in that cooling behavior. Scientists describe the result as evidence that Pluto's haze controls the atmospheric heat balance. In plain English, that means the haze is not some minor side effect. It is one of the main reasons Pluto's atmosphere behaves the way it does. This is one of those discoveries that sounds small if you rush past it. Do not rush past it, because what it means is extraordinary. Pluto seems to host a climate mechanism unlike anything else confirmed in our solar system. A tiny world in deep cold, with a thin atmosphere and almost no energy coming in, has still managed to evolve a system where haze particles dominate the thermal behavior of the sky above it. That is not just another Pluto fact. That is a whole warning to science. It says that distant worlds can run by rules we have barely started to imagine. And once you let that sink in, Pluto stops being a curiosity again. It becomes a message from the outer solar system, a message that says we have been underestimating these worlds, because the haze is only one layer of the story. The next layer is chemistry, and it may be even more haunting. High in Pluto's atmosphere, sunlight breaks apart methane molecules. The sunlight there is unbelievably weak compared with what reaches Earth, but it is still enough to drive chemistry over long spans of time. Those broken methane fragments can recombine into heavier hydrocarbons and other complex organic materials. Over time, this process helps create particles that drift downward through the atmosphere and settle onto the surface. These compounds are often called tholins, and they matter because they are part of the family of complex organic chemistry that scientists use to think about prebiotic conditions, not life itself, not proof of biology, but the kind of carbon-rich chemistry that becomes deeply interesting when you are asking how lifeless worlds prepare ingredients that, under other circumstances, might eventually feed living systems. That does not mean Pluto is alive. It almost certainly means the opposite. Pluto is far too cold, far too harsh, and far too chemically constrained at the surface for anything like known life to get started there. But that is what makes the place so eerie. For billions of years, Pluto may have been manufacturing and collecting complex organic material under a dark, frozen sky, only for that chemistry to remain suspended in a state of endless almostness. The ingredients can form, the reactions can proceed, the particles can fall like slow chemical snow. And yet the world is so cold that the story never crosses the line into biology. It is like watching a rehearsal for life on a stage where the final act never begins. If you're still with me, here is your second mission. Leave a comment with one word, Pluto, and hit subscribe if you want more scripts that turn real science into stories you can actually feel. And if this already has your brain spinning, share it now before the next part gets even stranger. Now think about what that means for scientists who study the early Earth. Long before oxygen filled our atmosphere, Earth was chemically very different from the planet we know now. Researchers, trying to understand those ancient conditions, often have to work backward from fragments, models, and indirect clues. But Pluto offers something unusual, a living example of nitrogen and hydrocarbon chemistry playing out on a real world today under extreme conditions over immense spans of time. Not the same as early Earth, not even close in temperature or habitability, but still a valuable natural laboratory for understanding what complex atmospheric chemistry can do when oxygen is absent and carbon-rich molecules are left to evolve in the open. That is one reason scientists take Pluto seriously. Not because it is a failed planet, not because it is a sentimental favorite, but because it may preserve physical and chemical processes in a state we cannot easily observe anywhere else. And then there is Charon. If Pluto were strange by itself, that would already be enough. But Pluto comes with a partner, and together they create one of the most unusual pairings in the solar system. Charon is not just another moon lazily circling a dominant planet. Pluto and Charon are locked together so tightly that they orbit a shared center of gravity outside Pluto's surface. They always show the same face to each other. If you stood on Pluto, Charon would hang in one place in the sky. If you stood on Charon, Pluto would do the same. It is less like a planet with a moon and more like a binary dance frozen into perfect repetition. For a long time, Charon looked simpler than Pluto, more muted, less dramatic. But even Charon turned out to be hiding secrets. Scientists had already suspected that material escaping from Pluto's atmosphere could end up on Charon. New Horizons hinted at that strange relationship, especially because Charon's poles showed dark reddish coloring. The suspicion was that methane escaping from Pluto drifts across space, gets trapped in Charon's cold polar regions during long periods of darkness, and then is altered by sunlight and radiation into more complex compounds that stain the surface. That idea alone is amazing if you slow down and picture it, a world losing part of its atmosphere, that material crossing the gap to another world, that second world storing it in deep freeze, then sunlight arriving later and chemically transforming it into something new. It sounds less like astronomy and more like one planet leaving fingerprints on another. And Webb added more to that story too. Using its infrared capabilities, researchers detected carbon dioxide and hydrogen peroxide on Charon's surface. Carbon dioxide appears most likely to come from material from the interior exposed by impacts, while the hydrogen peroxide points to surface ice being chemically altered by radiation. In other words, Charon is not just a passive ice sphere. It is a chemically processed world with a surface that records both internal history and the ongoing punishment of space. So now step back and look at the system as a whole. Pluto has a hazy atmosphere doing something unexpected with heat. Pluto is making complex organics in that atmosphere. Some atmospheric material escapes. Part of it may be captured by Charon. Charon's surface chemistry is being modified by cratering, radiation, and deposited material. This is not a dead pair of frozen leftovers. This is a dynamic system. Slow, yes. Cold, yes, but dynamic. That word matters because for decades, the outer solar system was too often imagined as a place where nothing really happens. The thinking went like this: go far enough from the sun, strip away heat, and you get stillness. Ancient relics, frozen debris, time capsules. But the farther we look, the more we realize that cold does not mean inactive. Sometimes cold means subtle. Sometimes it means the processes are slow enough that you only notice them when you observe carefully enough. And that is exactly what has happened with Pluto. New Horizons gave us the shock of first contact. Webb is giving us the slower shock of interpretation. One mission showed us the face, the other is helping us understand the behavior. The behavior is where Pluto becomes truly unsettling. Because once you accept that haze can cool an atmosphere this way, once you accept that organics can keep forming under these conditions, once you accept that neighboring worlds can exchange material and preserve chemistry over eons, you are forced into a bigger question. If Pluto is like this, how many other distant icy worlds are also hiding complex climate and chemistry under conditions we still barely understand? Pluto is not alone. It lives in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies, dwarf planets, and relics from the early solar system. Only a tiny fraction of these objects have been studied in real detail. Pluto is simply the one we know best because it is large, relatively bright, and got lucky enough to be visited. That means Pluto may not be an exception. It may be an introduction. And that possibility changes the emotional scale of the discovery. Because suddenly, this is not just a story about one small world surprising us. It is a story about a whole region of the solar system quietly waiting to rewrite the limits of what we think active can mean. Now imagine standing there. Not metaphorically. Actually picture it. You're on Pluto's surface. The sunlight is dim, like an intense star, rather than the warm flood we know on Earth. The ground beneath you is a land of exotic ice. Nitrogen. Methane. Water ice as hard as stone. The sky is thin and hazy, suspended between day and night in a kind of permanent gloom. Everything around you feels ancient but not dead, silent but not empty. Somewhere above, haze particles are doing their invisible work, absorbing the tiny trickle of sunlight and radiating heat away. Somewhere below, ices shift with the seasons. Somewhere across the black sky, Karen hangs motionless, an unmoving companion locked in eternal face-to-face gravity. It would not feel like the end of the solar system. It would feel like the edge of a much larger mystery. And then there are Pluto's landscapes, which deserve more attention than they usually get because they are not just beautiful, they are clues. Sputnik Planitia, that giant bright basin shaped like part of a heart, is one of the most astonishing terrains discovered by New Horizons. It appears relatively young, with remarkably few impact craters. That implies resurfacing. In other words, something has been refreshing that area on geological timescales. Nitrogen ice there seems capable of flowing and convecting slowly, almost like thick, frozen lava lamps moving over immense periods. Think about that. On a world this cold, one of the largest features we can see may still be slowly overturning itself. Elsewhere, New Horizons found dramatic ridges in the region called Tartarus dorsa, sometimes described as bladed terrain. These are huge ice formations, enormous compared with similar erosion features on Earth called penitents. The leading idea is that long-term erosion and sublimation shaped them, carving the surface into vast blade-like structures over time. Again, notice the pattern. Nothing about Pluto is nothing happened here. Even its most alien terrains are evidence that physical processes have been at work for ages, sculpting, sorting, moving, altering. And there are even larger unresolved questions still hanging over the planet. Some scientists think Pluto may hide a subsurface ocean beneath its crust. That idea remains debated, but it refuses to go away because several lines of evidence keep it alive. Surface features, the apparent behavior of Sputnik Planitia, and models of Pluto's interior all leave room for the possibility that somewhere deep below the frozen shell, liquid water may persist. If that is true, the psychological effect of Pluto changes again. It stops being just a frozen atmospheric oddity. It becomes one more member of a growing class of icy worlds that may hold hidden internal complexity where we once imagined none. And no, that does not mean there are fish swimming under Pluto's crust, but it does mean the solar system keeps finding ways to make seemingly impossible environments physically plausible. We keep meeting worlds that should have been simple, and they keep refusing to be simple. That might be the real lesson of Pluto. Not that it deserves pity for losing the planet label, not even that it deserves redemption, but that the universe does not care about the boxes we put things in. Call Pluto a planet, a dwarf planet, a Kuiper Belt object, or something else entirely. None of those labels change what it is actually doing out there. None of them change the haze cooling its atmosphere. None of them change the chemistry painting Karen's poles. None of them change the glaciers, the mountains, the strange terrains, or the possibility of hidden internal warmth. Reality is under no obligation to become less astonishing just because our vocabulary becomes more precise. And maybe that is why Pluto keeps capturing people's imagination, not because it was demoted, but because it keeps fighting its way back into significance through evidence. Every time we think the story is over, Pluto finds a new way to continue it. If this is the kind of space story you want more of, do something different this time. Save this video so you can come back to it later, subscribe before you forget, and send it to the one person you know who loves the words that makes no sense in the best possible way. There is also something deeply human about the way this discovery happened. New Horizons flew past Pluto in 2015 and transformed our view of the planet in a matter of hours. Webb, launched years later, did something just as important in a very different way. It did not race by, it waited, it watched. It separated faint signals from noise and pulled meaning out of light that had traveled across billions of miles. The contrast matters, because it reminds us that science does not move in one style. Sometimes discovery is dramatic, like a spacecraft, revealing mountains where nobody expected them. Sometimes it is patient, like a telescope confirming that haze particles are rewriting the rules of a distant atmosphere. And often the deepest breakthroughs happen when those two styles meet. A flyby gives you the shock, a telescope gives you the explanation. Together, they give you a world. That world, in Pluto's case, is becoming harder and harder to dismiss. Even the phrase Pluto, for the first time, carries a strange truth now. We discovered Pluto almost a century ago. We flew by it in 2015. And yet, in another sense, we are still seeing Pluto for the first time. Each new instrument reveals a layer the older ones could not. Each new observation replaces a cartoon version of Pluto with something richer, sharper, and far less predictable. So when people say James Webb just saw Pluto for the first time, what they really mean is this: Webb has seen a version of Pluto no previous telescope could truly reveal. Not just its presence, its behavior, its temperature balance, its chemistry. its relationship with Charon, its place in a larger class of icy worlds we barely know. And that is why this matters beyond Pluto itself. Because astronomy is not just about naming what is out there. It is about learning how many ways a world can exist. Earth gave us one example of what a world can be. Mars gave us another. Titan gave us another. Europa, Enceladus, Triton, Venus, Mercury, exoplanets around other stars, each one keeps expanding the list. Pluto now adds a version of climate that seems to depend on haze-driven cooling in a way we had not confirmed before. That is not trivia. That is a new entry in the catalog of possible worlds. And every time that catalog grows, our sense of what is normal gets smaller. Which brings us to the most important emotional point in this entire story. Pluto was once treated like the solar system's punchline. Too small, too far, too cold, too irrelevant, but the universe does not waste places. We waste our attention. Pluto was never empty of meaning. We were just blind to it for a long time. Now we know better. We know that a thin blue haze can dominate the heat balance of a world almost 4 billion miles from the sun. We know that complex organic chemistry can drift through that atmosphere and settle onto the surface below. We know that Pluto and Charon exchange material in a relationship. Unlike anything else we see quite the same way nearby. We know that Charon itself carries a chemistry shaped by impacts and radiation. We know Pluto's surface is carved by active or once active processes that still force scientists to argue, revise, and rethink. And we know that one of the most powerful telescopes ever built is still helping us pull meaning out of that darkness. That should leave you with a feeling that is bigger than surprise. It should leave you with humility. Because if Pluto can do this, then what is waiting on the next dim world we have not yet studied properly? How many other icy bodies are out there with atmospheres that behave strangely, with chemistry we have not imagined, with interactions that only look impossible because our tools have not been good enough yet? The Kuiper Belt may hold hundreds of thousands of objects larger than many familiar moons, and beyond that lies an even deeper reservoir of distant icy bodies. We have barely scratched the surface. We have flown close to only a couple of members of that outer population. Almost everything else remains unresolved, underobserved, and full of possibility. That means Pluto is not the end of the map. It is the sign that says the real map has barely been drawn. And maybe that is why this discovery feels so powerful. Not because it gives us closure, but because it does the exact opposite. It opens the door wider. It takes a world most people think they already understand and turns it back into a question. A cold question. A beautiful question. A question hanging at the edge of sunlight. How can something so small and so distant still be this alive with physics? That is the gift Pluto keeps giving science. It keeps forcing us to replace certainty with wonder. And in astronomy, that is usually how the next great story begins. So the next time someone shrugs and calls Pluto just a dwarf planet, remember what that little world is doing right now in the dark. Remember the mountains, the glaciers, the haze, the chemistry, the stolen atmosphere staining a neighboring moon, and the telescope far from Earth catching heat from a place the sun barely reaches. Remember that Pluto is not trying to be important. It just is. And the more honestly we look at it, the stranger and more magnificent it becomes. If this changed the way you see Pluto, make this final move count. Like the video, if you learned something real, subscribe if you want the next space mystery explained without the nonsense, and share this with someone who needs to know that the edge of the solar system is anything but quiet. Because out there, in the freezing dark beyond Neptune, a world we thought we understood is still rewriting its story. And the most exciting part is that it may only be the beginning